right, good morning. We are going to be looking at chapter 26. We've looked at the first portion of chapter 26. We've started looking at circuits that have some number of resistors. Those resistors could be in series, they could be in parallel. We've looked at ways to go in and determine for a variety of circuits with resistors in them, what are the voltages for each one of the individual resistors, and what are the currents, how much current is passing through each resistor. Once we have those, we can calculate the power. Now for a resistor, what power essentially is, power is an energy rate. So the power for a resistor is the rate at which electrical energy, which is sourced from the battery, ends up being converted into thermal energy. So you can think of a resistor is going to heat something up, right? We're not going to get that energy back. Once we've used that energy in the resistor, that heat is gone. That's thermal energy that's spread around through different objects now. They're just kind of heating up. The energy thermalizes. So now in the second half of the chapter, what we're going to be looking at here are circuits that contain not just a resistor, but also a capacitor. So this takes us back to chapter 24, where we studied the properties of capacitors. Now at that time in chapter 24, when we first looked at capacitors, we didn't really ask about the process of charging a capacitor. What we did was we said, how much charge eventually will end up on this capacitor if I connect it to a battery? Now we're ready, here in chapter 26, to actually set up a circuit. So I've got a battery. This is listed as having some kind of an EMF. Now for EMF, that's equivalent to asking what the voltage is on the battery. So I'm using those interchangeably. So the diagrams from the textbook are going to have these little squiggly E's in them, but I'm typically for now just going to call that voltage. So there's a resistor, there's a capacitor, here's a switch. So it looks very much like the other circuits we've been looking at, except this time there's a capacitor. Now, let's think about what happens then as we close the switch. When we close the switch, current begins to flow. Now they moved the battery, they flipped it around, I think. Anyway, they've got the battery oriented so that the current is going to be traveling in this direction. What you would think of mathematically as the positive direction for turning or counterclockwise. And that's because of the plates on the battery, the plus and minus plates. Now, when we close the switch, we're going to have current going through everything in that loop. It's a pretty simple circuit. It's still just one loop. And that means that if I measure the current passing through the battery, that's going to match the current going through the capacitor, that's going to match the current going through the resistor. Now, as we mentioned, current going through a resistor, it's just going to generate a bunch of thermal energy. The capacitor is the new guy here, so let's ask what effect is the capacitor going to have on this circuit. And what the capacitor will do is the capacitor is going to charge. And as the capacitor begins to build up positive charge on this plate and negative charge on this plate, eventually the voltage, due to the presence of that charge, the voltage from the capacitor will match the voltage from the battery, and the capacitor will stop charging. Now, the actual function describing that looks something like this. It's actually an exponential function, but it's kind of flipped over. You know, this is what a standard exponential would look like down here. This is kind of taking that exponential drop-off and flipping the function over. And so what happens here is, if we look now at the voltage on the capacitor as a function of time, what it's saying is that the capacitor's voltage will steadily increase, and it'll asymptotically approach some final value. Now eventually in this circuit, the capacitor will have the same voltage as the battery. So this dashed line that we've got listed here, this asymptote, is going to be the voltage of whatever the power supply is. Meanwhile, what's happening with the current? So this is telling us what is happening in terms of charging the capacitor. The voltage across the capacitor is going to be proportional to how much charge is there. So the capacitor charges and builds up voltage. Meanwhile, the current current decreases. So the current is going to start off high and then it's going to drop off. The argument here is, hey, when I first close the switch, the capacitor has no effect. At least initially, right at t equals 0, capacitor doesn't have any charge on it. So if the capacitor doesn't have any charge on it, at least initially it looks as if there's just a complete circuit over here. Once the charge does begin to build up on the capacitor, then it becomes pretty noticeable to the rest of the circuit. Oh, something's happening over there. There's actually a buildup of voltage at this location. If the voltage increases here, there's going to be less voltage available driving current through the resistor. And so charge is increasing according to this flipped over exponential, and the current is dropping off. Now, we need to, let me look ahead just a bit. Let's see what other slides we have. We may want to come back to this one. Or let's see, here we go. These are actually the equations that we're working from. We showed what the functions look like, and where those functions are coming from mathematically is this. If I look at that circuit, what I can say is the voltage boost, which we talked about last lecture. So the voltage boost in this circuit is the voltage from the battery. And then I've got two devices that represent voltage drops. So now, not only are the resistors voltage drops, but the capacitor is a voltage drop. And that's because the voltage across the capacitor is building in opposition to the voltage across the battery. So voltage of the battery equals the voltage of the resistor plus the voltage of the capacitor. Now, what we can do in this equation is, there's actually some complication here. Let's take a look and see. The V, the R, and the C, those are all constants. So the V, or the script E that's shown here, the V, the voltage in the battery, depends on how we built the battery. It's direct voltage. It's going to remain constant. The resistance in the resistor, that's a fixed value. So again, that's something that's just going to stay constant through the whole process here. And then the capacitance also is going to depend on the properties of the capacitor. So those things are all constants. Now, what this diagram hasn't shown, but what we want to make clear, is that there are two functions here of time. Q is a function of time. The Q on the capacitor starts out at 0 and eventually rises to some final value. The current is also a function of time. So the current is going to start out initially very high and then exponentially drop off. So again, if we go back to our circuit here, this graph, it's in terms of voltage, but it's proportional to charge. Charge is going to be changing as a function of time. Current is going to be changing as a function of time. So that tells us that what we have then is we have two of these variables, I and Q, are actually functions of time. And to solve this equation, what we do is we say that Q and I are related. Q is going to be the time derivative oh, they've got that wrong. Okay. Okay, so there's an error in the slide here. This is supposed to say I is equal to dq dt. It's the current that is the ratio of dq to dt. It's the time derivative of q, so All right, Giancolli slipped up on this one, or whoever put this slide together. So again, correction here. This is I is equal to dq dt. I didn't catch that when I was going through their slides. So what happens is this. What we can do is we can set I equal to the time derivative of charge, and then we can solve what's called a differential equation. Now, if you've taken differential equations, this could be one of the examples that they've shown you. When you do take differential equations, you're going to see stuff like this all the time. You guys aren't responsible for solving this. You are responsible for being able to take the solution and show that this solution really works. We'll do that a little farther into our discussion. We'll actually go back and take a look at these solutions and show that they really work. Okay, so anyway, now in this solution that we had on the previous page, if we now convert that into voltage, it says the voltage on the capacitor is going to be varying by this function. So that stuff in the parentheses, that's the flipped upside down exponential, the 1 minus e to the minus t over RC, where R and C are the resistance and the capacitance. Now, you guys have been looking at exponential functions a lot, and I think you've heard me say this before in Physics 4a too. It's worth familiarizing yourself with how these exponential functions work. They show up all over the place. So we do want to be familiar with how they work. And there's actually, this is where those plots looked really nice. I'm going to go back and pick those up. Right here, these flipped over exponential increasing functions, when we have gone to one time constant, they have gone to 67% of their value, of their peak value. So again, this is like saying, well, if it was a half-life or something, it would be the amount of time it takes to get to 50% of the peak value, but we're not working in base 2, we're working in base E. And you guys all know how important E is in being able to take derivatives, and so anyway, E really is the natural base, you know, that's the base that shows up in all of our differentiation and integrating. So familiarize yourself. So an exponential drop-off through one time constant drops to 1 over E, or 37% of the original value. Okay, we'll see this. This is going to keep coming up. All right. Now, for this, we kind of have to flip back and forth quickly. They've got the charge. All right, they started with that differential equation. That's the expression for how the charge on the capacitor is varying as a function of time. This is how the voltage on the capacitor is varying as a function of time. And this is how the current through the capacitor is varying as a function of time. And as we said, they got it right this time. So I is equal to dq divided by dt, and from the q function that we had before, we can take that derivative and we find out that that's what the current is going to look like as a function of time. Okay, it's a lot of pieces. So we're keeping track of charge, current, voltage on the capacitor, voltage on the resistor, voltage on the, well, that's a constant on the voltage on the battery, but you can see there are a number of items that are changing here as time goes on. All right, oh, here we go. So here's my own diagram of all this, and what we've got in this one, what we have in the diagram here is, well, this is the charge as a function of time. Now, this is charge variable. For the peak charge, the ultimate charge that the capacitor acquires, I'm calling that Q naught. Now, this notation is a little different. Usually when we put a naught on something, it's referred to the initial quantity. But you'll see why the Q naught here is actually pretty handy. We saw this before with the peak current and the peak voltages, had a little naught out to the side here, a little 0. So I'm going to call this Q naught. And from chapter 24, we already know that the eventual charge on the capacitor is going to equal its capacitance times whatever the voltage is in the battery. Okay. And the voltage of the battery is V. There's our circuit over here. I flipped the battery back around. I guess that's how I'm used to drawing them. Now what's going to happen with the charge is our charge function is right here. So that's the same function that they drew out. I'm going to claim this is written more simply, but probably not. Here is Q as a function of time, and it's equal to this final value, and there's that time-dependent function, the 1 minus e to the minus t over tau. That gives us that curve. That's what that curve looks like. The Q naught is equal to CV, and the time constant is given by R times C, and again we'll see that in some later examples that really works. So when I take a resistance times a capacitance, it actually gives me units of time. That tells me that an ohm times a farad is a second. So if you want to tell your friends you'll be there in 10 seconds, you can say, you know, hold off, I'll be there in 10 ohm farads, because it's the same thing as a second. And so ohm farads are going to give us the time constant in seconds. Now, here is this exponential stuff. What happens is, when I'm dealing with an exponential flipped over function, the Q function, after one time constant has gone by, I will be at 63% of the peak value. After 2 time constants, that goes to 86%. After 3 time constants, it goes to 95. Now, what you may be thinking is, well, when does this capacitor ever get fully charged? And I guess there's 2 ways of thinking of this. The mathematical answer, I guess, is when does this function ever reach the asymptote? And it never does. But in physical terms, you're really saying, when does that last electron finally drop onto that plate of that capacitor? So there is going to be some point at which the capacitor is fully charged, and once 5 or 6 time constants have gone by, then it's going to be 99.9 something percent, and at that point we just say, hey, it's fully charged, basically. So again, 63, 86, 95%. Now for the current, which is dropping off as a function of time, and we have got that derivation here too. So this was what the charge looks like, the charge dependence, or the time dependence of the charge. Here is the current function, I as a function of t, and here we've got, when we take that derivative, we've got something that's just dropping off exponentially. So what's happening here is the current's dropping off exponentially. Just give me 1 second. All right, I'm right back. So these are the 2 time-dependent functions that we were talking about. Now, we determined what Q naught was in terms of the properties of capacitors. Now what we can do is we can find out what I naught is going to be. I naught is going to be whatever is out in front of that exponential function, and when we substitute in the values for Q naught, it turns out it's V over R, and we go, oh, there we go. So the current starts off as if there's no capacitor there at all. Initially, the current value is given by V over R. All right, questions on any of that? So that's what's happening with this capacitor as we charge this. At t equals 0, we close the switch. And then we watch to see how the charge builds up on the capacitor plates. And here we're watching how the current drops off. Now the charge applies to the capacitor, but the current applies to everybody in the circuit. Everybody in the circuit is experiencing the current. There's current going through the battery, there's current going through the resistor, there's current going through the capacitor. Even though nothing crosses from one plate to the other, the rate at which charges appear is equal to the current. And on the opposite side, the rate at which charge is disappearing from this plate, or negative charge is showing up, is equal to the current. So again, we can treat the capacitors as if there's a current going right through them. All right, we may come back to this. This is a good reference set of diagrams. Dropping off exponentially, 37%, 14%, 5%. Notice that these two functions that we keep bringing up, the ones in the brackets, that they're, in some sense, we could say they're complementary, in that if I look at how far the charge is relative to its peak value, 63%, the current has then dropped to 37%. Those two numbers always add up to 100. Okay, so that's handy. That's something you can watch for when you're doing the homework problems and seeing how this is all behaving. All right, now in addition, looks like a duplicate from the last slide. The last slide was looking at charge and current, but this slide is looking at voltage as a function of time across the capacitor and voltage across the resistor as a function of time. Now the voltage across the capacitor is given by Q over C. For these circuits, Q is a function of time and so is the voltage. C is a constant. So the plot looks exactly like the charge plot did. It's this flipped over exponential. And what we find is if, now I put a V naught here to try and emphasize this is a constant. The voltage across the capacitor is going to equal V naught times that flipped upside down piece. Whereas the voltage across the resistor, when we go and substitute all these expressions in, is given by V naught e to the minus t over tau. So again, they're complementary functions. The voltage is divided between the resistor and the capacitor at all times, but it's not fixed. It's time dependent. And that's what it says down here. So it's saying voltage across the resistor is a function of time, voltage across the capacitor is a function of time, but at each instant in time, they continually add together to be the voltage across the battery. All right, questions on any of that? All right. Now here's a problem that's given in the textbook, or in the slides for the textbook. And so let's go ahead and take a look at this. It does look like they've permanently flipped over their batteries. I need to start following that approach maybe. So here's the battery. It's got some voltage. And here's the switch, the resistor, and the capacitor. Same as before. So it's a simple one-loop RC circuit. Now here they're starting to give us some numbers. And they want us to solve, it's actually a lot of stuff here that they want us to be solving. They want us to solve A, B, C, D, E, and F. So let's see what that looks like. First of all, they're telling us some properties of what's in here. The capacitor is at 0.30 microfarad, which is like 300 nanofarad. And the resistor is at 20 kiloohms, 20,000 ohms. And the batteries, there it is, EMF, or voltage, is 12 volts. So they gave us the values for the circuit. And from that, they want us to go in and start solving for everything. So they want us to solve for the time constant. Now the time constant, again, is going to give us an idea of how fast or how slow, how much time is it going to take to charge up that capacitor. They want us to figure out what eventually will be the maximum charge on the capacitor. And they want us they want us to figure this out. How long is it going to take until the capacitor has 99% of its charge? Now, this is one of those things where, hey, once it gets to 99%, that's kind of like the capacitor's charged, right? So anyway, we'll see how long it's taking for this particular capacitor to charge in this particular circuit. And then they want to ask questions about when the current, when the charge is half maximum value. So when the capacitor is halfway charged, what's the current? And then later on they say, what's the maximum current? There's just a long list here. And then when the current is at 20% of its maximum value, what's the charge going to be like on the capacitor? So let's see how many of those we can answer. I'm thinking we want to try and answer them all. So let's get started here. Here's that same circuit. I flipped it over. I got rid of their EMF symbol and replaced it with a voltage symbol. So eventually I'll cave in and start writing it the way they're writing it. And I put a couple of other items in here. I put in a couple of lines showing that the current, just reminding myself, the current's going through each one of these components, the capacitor, the resistor, and the battery. And then I drew in the graph for the charge. That always feels like the most important graph, is how much charge is there on the capacitor as a function of time. And I put some plus and minus signs to show the polarity of the capacitor. Because we're going to find out, it actually becomes important, keeping track in these diagrams, which plate is acquiring a positive charge and which plate on the capacitor is acquiring a negative charge. And I'm going to look at the battery to see how that works. So the positive plate of the capacitor is connected to the positive terminal on the battery. If just for a moment we step back and ask about electrons, electrons are going to be in the opposite direction. So the battery is pumping electrons to the negative plate, pulling electrons into the positive plate. So these electrons that get produced are, the whole series of electrons all lined up, all start to move through the circuit. They're going to make their way through the resistor. Those electrons are going to end up building up on that plate. And then electrons are going to get pulled off of that plate. That's going to leave it positive. Okay. So we do want to be able to figure out orientations of charges on these. Now, we said that with the time constant for charging, that's going to tell us the amount of time it takes for the charges to reach 63% of the peak value. And so the capacitance is 300 nanofarads, the resistance is 20,000 ohms, the voltage is 12 volts. It's easy enough to plug the numbers in. We want to pause and make sure that we understand what we're doing here, but there is tau is equal to, that's a Greek letter for the time constant, R times C. And the R value is 20 kiloohms, the capacitance is 300 nanofarads. I thought it'd be a good time to start practicing using more and more of these prefixes. And so the kilo is 10 to the 3, the nano is 10 to the minus 9. When I used those in my calculation, what I ended up with was 6.0 milliseconds. That's 10 to the minus 3. I didn't write that in, but I could have. So anyway, the time constant is a fraction of a second. Turns out that the time constant here is actually about 6 milliseconds. The resistance is, it's a fair amount of resistance. It's not a lot of capacitance. So if you think about this, what would determine how fast a capacitor charges? So let's see, if I've got more resistance in the circuit, that's going to slow down, it's going to lower the current. It's going to take more time to charge my capacitor. So it makes sense. More resistance is going to take more time. Similarly, if the capacitance goes up, so if the capacitance is higher, that would say that I've got more room on those plates, I can store more charge. It's going to take longer to fill the capacitor if it's got more capacity or more capacitance. So it turns out that it's just the product of those two effects. So that's my time constant. Now, what about Q naught? What's the peak value of the charge that we're going to end up with? And that's given by C times V. Again, we've seen that since chapter 24. I can put those numbers in and determine that the asymptotic value for the charge, as I'm charging the capacitor, is 3.60 microcoulombs. Okay, you can check numbers on these too. If you see an error that I've made, send me a message, let me know, and I'll try and get that corrected and sent out to everybody. So that's the peak charge. Now, the next part of this was asking, well, it took one time constant to get to 63%. How much time is it going to take, how many time constants, and how much time would it take to reach 99%? 99% feels like it's kind of fully charged. And so what I did was, I came down to this formula, this time-dependent formula, and said, look, what I'm really asking is, when does that time-dependent function inside the parentheses, when does that equal 99%? When does that equal 0.99? And so I took that, set it equal to 0.99. Now, there's a 1 here, and so that tells me that my e to the minus t over tau needs to be 1%, or 1 over 100, or 0.01. So I'm looking for where that is equal to 100th. And if I do a natural logarithm on both sides, so you guys remember all your exponentiation and taking logarithm sort of algebra, because it'll show up. So this is a good chance to get some practice doing that. So I'm getting minus t over tau is equal to the natural log of 0.010, and at least at first I'm thinking, uh-oh, there's a minus sign. Is that a problem? And it's not a problem, because a logarithm of something less than 1 is negative. So now, if you're like me and you're frightened of minus signs and errors coming from minus signs, another one of my tricks, another trick out there, not necessarily mine, is if I want to introduce a minus sign, I take the inverse of whatever is inside the logarithm. So that's what I've done. Instead of writing this as the logarithm of 0.01, I wrote it as the logarithm of 100, and that brings out a minus sign, which allowed me to cancel the minus sign in my formula. So now I've got a formula that says, hey, the amount of time it's going to take to reach just 1%, to come within 1% of my asymptotic value. Let's say it that way. So I'm waiting for the capacitor to come within 1% of its final value. And that can be written as the time constant times the logarithm of 1. Now, before we even evaluate the time constant, I guess we did that up here, I can right away say that that's going to take 4.61 time constants. So I can always write these expressions in terms of some number of time constants. And so that's kind of interesting, by the time I get up to even 5 time constants, it's going to be within 1% of its final charge. It's going to be above and beyond 99% of the charge. Now, the last step was to just put the time constant back in. That worked out to be 27.7 milliseconds. So you can see, for this circuit, the capacitor charged, well, depending on what your timing issues are, 27.7 milliseconds seems pretty fast. Okay, so that's pretty quick. That thing's charged up. Didn't take too much time. All right? All right, let's continue on with the rest of the problem. There was like more. We did A, B, C. Now we're going to do D, E, F. In part D, they are asking, at the time when the current is half its maximum value, what will the charge be? Or maybe it was the other way around. Anyway, this is how it works. I wrote down the two equations. Here is Q as a function of time. Here is I as a function of time. And I've written them in terms of the peak value of Q and the peak value of current. And I can solve for the peak value of current. It's V over R. And that gave me 600 microamps. So it's really a pretty tiny current. It's It's not an enormous amount of current that we're seeing in this particular circuit. And then what I decided was, since these are complementary functions, what I'm really looking for is when does that become 1/2? If they want to know at what time does the charge become half of its final value, that's going to be the same thing as asking when does the current drop to 1/2 of its value. And so recognizing how these functions work, I said what I'm looking for is Q is equal to 1/2 of Q naught, I is equal to 1/2 of I naught. And then I used the same sort of approach to solve that. What I did was I set this equal to a factor of 1/2, and then I flipped it over to get rid of the minus sign. That became an ln of 2. And what that turned out to be was 0.693 time constants. So again, I can write this in terms of how many time constants is it going to take, and then that became some number of milliseconds. All right. Now in part E, it asked what is the peak current, and I ended up already having solved that in the previous problem. So that was taken care of. And then finally, they asked something a little different here. They didn't ask when are things 50 and 50. They asked what happens if the current is 20% of its original value. And if the current function has dropped to 20%, what that tells me is that the charge must be at 80%. So recognizing that these two functions, the one for current, the one for charge, are complements of each other, together they always add up to 1, saved me a lot of math. I didn't have to do much math on that final part, on part F at all. Once they told me the current was at 20%, then I knew that the charge was at 80% of its peak value, and I could easily plug that into my charge that I previously calculated and get 2.88 microcoulombs. Okay. All right. So that's kind of it. That's a pretty good example with a number of parts going on. So that's a good example to look at. All right, now what we have seen so far with these RC circuits is that we've got this battery, we've got the capacitor, we've got the resistor. We're going to charge up the capacitor, and I was interested in taking a look at power for each one of the components. Turns out that keeping track of the power, the rate at which energy is going into the circuit, the rate at which energy is being thermalized in the resistor, the rate at which energy is being stored in the capacitor, those are all interesting questions. And so I wrote down these expressions. We've solved this before and shown that the current behaves like an exponential drop-off, and that the current applies to every component. The current through the resistor, current through the capacitor, current through the battery, they're all the same thing. They're all the same time-dependent function. Now, the voltage across the resistor and the capacitor are time-dependent, and they have these two different time dependencies to them. So we also had shown that on some previous slides as to how the voltage on the capacitor and the voltage on the resistor are related. All right, so far so good. Now, the voltage across the battery is just fixed, and I think for the purposes of this slide, I got the V naught initially at least. At the very last stages, I kind of dropped it back to V. But the V naught or the V is keeping track of the voltage on the battery. All right, now since I've got the current and the voltages determined for the capacitor and the resistor and the battery, what that means is that I can calculate the rate at which energy is being used in the resistor. I can calculate the rate at which energy is being stored in the capacitor. I can calculate the rate at which energy is coming out of the battery. What are you guys guessing is going to be true about those three energy rates, those three powers And it's going to have to be the case that if we calculate the rate of energy coming out of the battery as a function of time, each instant in time, that's going to match, adding together the energy rate of thermal energy in the resistor and the rate of energy storage in the capacitor. Okay, it's got to, right? Energy is going to get conserved in these circuits, so those numbers should match up. So I did that. What I did is I wrote down an expression for power for the resistor and one for the capacitor. And what we had said in an earlier lecture was that P equals VI works for everything. It works for batteries, it works for capacitors, it works for resistors. So I can use VI to calculate the power of any device. So I took specifically the voltage function for the resistor. I got to get the right voltage expression here. And then I picked up the current. Now the current for the resistor is just, that's for all components. Every component's going to have that same expression. So I took that product, and what I ended up with were these two constants, V0 and I0, and then I had two factors of exponential. So that's saying what's going on in the resistor is the voltage is dropping exponentially, the current's dropping exponentially, and that says the power is dropping extra exponentially. It's dropping like two factors of that exponential drop-off. So I did a quick graph. It's not, I didn't label the axes or anything. I'm going to lose a bunch of points on this. But basically the power is going to drop off exponentially. As the current slows down, the resistor is thermalizing less and less energy. All right. Now for the capacitor, how does that compare? And for the capacitor, I took the voltage across the capacitor, that expression that we had looked at, and multiplied that by my current. Now this one still had two time-dependent functions. One of those was exponentially dropping off, but one of them was the flipped over function. So that's kind of interesting, that it's not two factors of the same item. What that gives us for the power, the rate at which energy is being stored in the capacitor, is a function that looks like this. Initially, we're not storing much energy in the capacitor because there's not much voltage built up. There's not much charge there initially. And so those first charges that show up on the capacitor, they're really not storing a lot of energy. As we store more and more charges on the capacitor, the power rate goes up. We're storing energy at a faster and faster rate, but then that drops off too because eventually the current shuts down. So two different shaped functions, but we could ask this question. If I was to calculate the area under each of these two functions, what would that be? What would it be if I calculated the area under this resistor function, the power in the resistor, and what would it be if I calculated the area under the power, the energy storage in the capacitor? And if I integrate power over time, I'm going to get energy. So the area under those functions corresponds to the total amount of energy. For the resistor, that's going to be the total amount of thermal energy that is generated during the charging process. For the capacitor, that should tell us, that area under that curve, it should tell us how much energy is stored in the capacitor once it's fully charged. So let's try those two expressions. Now I came down here and I wrote down energy. I'm using U to keep track of energy. That's something we've used for potential energy before. This time I'm just using it as a general sort of energy designation. So for the resistor, if I want to calculate how much energy goes thermal during the charging process, here is the energy of the resistor. I can take the power function, which is right here, and integrate that over time. And for my limits of integration, I'm going to go from 0 to infinity. So I'm going to allow for the whole charging process. It can last as long as it wants, because what's going to happen here is the bulk of the thermal energy is going to get generated early on. As time goes on, I'm going to be generating less and less thermal energy. Integrating all the way out to infinity, that's fine. So it's going to pick up those last little bits of thermal energy. And so this is going to be the integral of, remember I've got two factors of this, so that's showing up as e to the minus 2 t over tau dt, and I carried out the integration. Now it's an exponential function, so the integration is not so difficult. It's going to give me, well, here are my factors of v naught, I naught, and then I'm going to get a factor of tau over 2, and then I'm going to get the exponential back again, and here's another one of those tricks to try and avoid minus signs. Instead of writing the minus sign here and taking limits where I take minus of minus to get something positive, what I can do is I can eliminate the minus sign here by flipping my limits. So limits that used to be 0 to infinity, I switch those to infinity to 0. And again, it's just a trick to eliminate that minus sign. Now, when I calculate that, try that and see if it makes these evaluations of integrals faster. V naught, I naught, tau over 2, I'm going to get 1 at my 0 limit, and I'm going to get 0 at the infinity limit. So if I take the V naught and the I naught and the tau over 2, and 1 minus 0 is just 1, if I evaluate all of those, let's see, the V naught I'm just calling V, the I naught was V over R, the tau was R times C. I'm getting some cancellation, and what I've ended up with is 1/2 C V squared. Now that's an interesting result, because just jumping ahead quickly, when I carry out the same calculation for the energy stored in the capacitor by the time I've completely charged the capacitor, how much energy will be stored there, it's also 1/2 CV squared. You may remember that formula from chapter 24. So this is, I don't know, is this discouraging maybe? It says this, it says, I would like to store a certain amount of energy in my capacitor. Is there a way that I could take a battery, hook it up to a capacitor, and transfer that energy 100% efficiently? Can I take a given amount of energy stored in my battery, available in my battery, and efficiently transfer that over so that the capacitor has that very same amount of energy? And these calculations are saying no. They're saying what's going to happen is you're going to charge up the capacitor so that it has a energy of 1/2 C times V squared, but along the way you're also going to generate thermal energy in the resistor, and that's going to be 1/2 CV squared. And that looks to me like half the energy just comes out as thermal energy. In order to transfer 100 joules of energy from my battery into, if I try to transfer 100 joules of energy from my battery to the capacitor, only 50 joules get to the capacitor and 50 joules go out as thermal energy in the resistance. Okay, so again, it's a little bit disappointing. We could go through this second integration. It's a little more involved. It's a product of these two functions, so I have two terms that I'm integrating. If you just pay attention to all those terms, though, you find out you get the very same result. So it turns out the area under that function and the area under that function, they're the same value for charging a capacitor. Now you might be thinking, okay, I don't want to use half my energy charge every time I charge a capacitor in my circuit. I don't want to have an equal amount of energy that just goes thermal. That's useless. What if I just take the resistor out and go back to chapter 24? Is that a possibility? And it's not, right? Because I can't take all the resistance out of the circuit. Even if I take this resistor out, there's still going to be resistance in the wiring. So even if I take out the designated resistor symbol, that doesn't mean there's no resistance in the wiring. The wires are going to have some kind of resistance to them. So I'm kind of stuck with this resistor. Now, it does seem like a good idea. If we put less resistance in, will putting less resistance in help us? will that allow us to use less energy to charge the capacitor? And it turns out it doesn't. Notice that putting less resistance in means the capacitor charges more rapidly, or not no resistance, let's say this. If we bring the resistor lower and lower and lower and try and get the resistance way, way down, the capacitor charges faster and faster. So it speeds up the process. But notice that when we calculate the energy that goes into thermal energy from the resistor, that's independent of what the value of R is. The amount of energy that goes thermal is always going to be 1/2. It doesn't matter if we use a big resistor or a little resistor, we're still going to use up half the energy in the process of charging our capacitor. All right? Everybody's okay with that? Kind of sad and disappointing, I guess, but it's good to know, right? It's good to know up front that this is what we are up against. All right, good set of calculations here too. I'm going to say, this slide and the ones before that I had written up, those are all good to go through and take a look at. All right, now what we're going to do here is a little different process here. Notice that the circuit that we're working with this time, it doesn't have a battery. So what's happened here is we have a capacitor, it's already been charged, right? We charged it, we set it somewhere, we went out, got some lunch, we came back, the capacitor is there, it's still charged. And we just have decided, let's go ahead and discharge that capacitor. Now, when we discharge the capacitor, we're going to close that switch at t = 0. We're going to connect the capacitor, put in some resistance. Even if we don't put a resistor in formally, there's still going to be the wiring. So there is going to be a resistance in the circuit. Now when I close the switch, what will happen is electrons which have been stored up here are going to be able to come off of that plate. We're going to have current travel everywhere in that circuit. Electrons nearby here begin to fill that plate. Electrons leave this one, and the capacitor discharges or de-energizes. So we're going to lose all that energy that was stored in the capacitor. What's going to happen to all the energy that we had stored in the capacitor? We could go back and do those power calculations again. If we do, I have a pretty good idea of what's going to happen. We're going to find out that the resistor now thermalizes all that energy. So all the energy that was stored in the capacitor, when we discharge it through a resistor, it's going to all be dissipated as heat. All right, good to know. Now, in this circuit, it's different. What they're going to tell us up front, we haven't really shown where this is coming from yet, but they're going to tell us that the charge now on the capacitor is going to drop off exponentially. Remember when it was charging, it was that flipped over exponential function, but this time it's just going to be a straight exponential drop off. It's going to be an exponential drop off towards 0. Capacitor is going to completely discharge. And look, we've got our time constant in there again. One time constant would be RC. Two time constants would be 2RC. Three time constants would be 3RC. And that says that by the time one time constant of time, that time length has gone by, we'll be down at 37%, two time constants at 14, three time constants at 5%. Okay, and I think before we calculated at 4.61 time constants, we'll be all the way down to 1%. Let's look at this some more, this discharging process here. So what they're writing here for the capacitor as it discharges, what we're finding is that once again the voltage across the capacitor is going to be dropping off with time. So the voltage across the capacitor is given as V naught e to the minus t over the time constant. Now the V naught in this case is the voltage we started with across the capacitor. So remember, the resistor initially was isolated. It was the capacitor that had charge, it had a voltage across it. If we go back to that circuit before, or the slide from before, what we've got now is, let's get out our voltmeters, right? So I've got my voltmeters ready to go here. If I measure the voltage across the capacitor, I'm measuring a V0. I'm measuring some kind of a voltage there. If I put my voltmeter across the resistor, it doesn't read anything, it reads 0. There's no current going through the resistor, and so the resistor doesn't have any voltage across it. When we close the switch, instantaneously we now have that voltage set up on the resistor. So suddenly the resistor has voltage across, and current will begin going through the resistor. And here it is. So if this is the voltage, now the previous slide showed the charge, this is showing the voltage, and now we're ready to calculate the current. Now I have a bit of an issue here too. So they are now defining current as negative dq/dt. And they're going to argue why they want you to use a minus sign. I would rather not go that route. I would rather stay with the definition of just dq/dt, not introduce the minus sign here. Now by not introducing the minus sign here, what's going to happen when we take that derivative is we're going to find out that the current is now negative. And you have to say, well, what would a negative current indicate? And I think that's useful. So one more look at our circuit here. When this capacitor was charging, which direction did the current come in? And when the capacitor was charging, the current was coming this way. So I know that because this is the positively charged plate. So when I look at that positively charged plate, the current was coming in when it was charged. In order to discharge, the current is going to reverse directions. I really like having the minus sign explicitly show up here to remind me that the current during the discharging process will have to be opposite in direction to what the current was during the charging process. And so that is why conceptually, I think it's better not to put the minus sign here. First of all, we're going to maintain consistency with our definition of current as being dq/dt. We're not going to change the definition of current. And then the minus sign that does show up over here reminds me that during the discharging process, the current's going to be going in the opposite direction compared with when the capacitor was charging. Okay, so anyway, that is my preference on that. And then here is my own write-up as to what's going on during the charging and discharging process. So what I've done here is I've drawn this diagram of the circuit. I'm trying to put both possibilities together. I'm going to put together a circuit where we can charge the capacitor and then we can discharge the capacitor. And so what I've done is I put two switches in. Now to get that capacitor charged, I close switch number 1. I close switch number 1, I build up a bunch of charge on this capacitor, and then I open switch number 1 back. And then the circuit's kind of stuck with there's a battery over here, but it's not connected up. And I've got a capacitor which is now charged. That's not connected up either. Now, during the charging process, so think of the loop on the left. I close that switch on the left, and during the charging process, the voltages of the capacitor and the resistor combined have to equal the voltage on the battery. So again, close that switch, voltage, get out the voltmeter, voltage across the capacitor plus voltage across the resistor. Those are my two voltage drops. They have to equal my voltage boost. Now, what that equation looks like then is the voltage across a capacitor is 1 over C times Q. And Q is going to be some function of time. Similarly, the voltage across the resistor is going to be given by R times I, where I is a function of time, and those two functions have to add together in a way where it gives me a fixed constant voltage. And that's kind of like before when we were saying those two functions are complementary to each other, and when I add the two functions together, they cancel out, they become a constant, and that's why those functions work. So this is the charging process, and we've already looked at this some, and the way we would solve this in a differential equations class is I would now take that I and replace it with dq dt. I'd replace it with the time derivative of the q function. So I've got the first derivative times a constant plus the function itself times a constant has to add up to be another constant. And there's kind of standard techniques for solving this particular type of differential equation. These are some of the most common differential equations that show up. Now, discharging the capacitor, that's going to happen when I close the switch on the right. So we've charged the capacitor, we've looked at that, we're done with that. Now what I want to do is close this switch. Well, when I close this switch, what's going to happen is the current is going to be in the opposite direction, right? So the current was going through the capacitor this direction when it was charging, but now the current's going to go this way. And it's going to form a loop on the right hand of this, the right side of this diagram. All right. Now, I've got this set up so that the resistor, or the resistance, during charging and discharging is the same. Doesn't have to be. It could be that I have other resistance over here during the charging process, and I have different resistors over here that only apply for the discharging process. So it doesn't have to be the same time constant. It doesn't have to be the same resistance. Now, if I look at the functions for discharging, or if I look at the differential equation, what it says is the two voltage drops now have to equal 0. Now that's funny. How could two voltage drops give me something that's 0? One of these voltage drops is actually going to have to be reversed. And that's another feature of where the charge is positive, but it's dropping off with time. The current is negative. So what that's saying is, when we close this switch, let's get our voltmeters out. The voltmeter here is going to read the voltage over the capacitor. Which side of the capacitor is at the higher voltage? You go, well, the positive side. So I've got a voltage across here, and this side is higher than this side. Now, what's the voltage across the resistor going to look like? And for the resistor, current's going to be going this way. This side is going to be higher than this side, and those are going to match. So the voltages are going to be, it's kind of like they're out of phase with each other. Because of the way the current, or rather, I guess, because the capacitor was already pre-charged before we started this part of the problem, the current and the charge aren't matching up. And by that, what I'm saying is the current coming into here, it's not building up positive charge, it's eliminating negative charge. In any case, the voltages here are going to add up to be 0, and that's what our differential equation says right here. Now this one's easy enough to solve. You could solve this in a Calc 3A or 3B class maybe. What you've got is just a first derivative of a function equal to the function itself times some constants. And so I wrote down the solution. The solution is that the charges are dropping off exponentially. That's what we expected. And that the current is also dropping off exponentially, but in a negative direction. And so these two functions here can be plugged back into this equation. When I do that, what I'm going to end up with is this formula right here, 1 over c times the charge as a function of time, minus, sorry about the minus sign, minus r times the current, and the current is this function right here. So this function that I've written here is coming from those two functions plus the equation above. So again, it's not so important to know all the details about the derivations on these. You should be able to use the results though and figure out, you know, how much time does it take for the current to drop a certain amount. Now, by recognizing that this has to cancel out to be 0, we can factor out the exponentials and we get an equation that's and the Q naughts. The equation says 1 over c is equal to r over tau. That's our verification that the time constant really is r times c. So the time constant we get for discharging has the same form to it as the time constant for charging. And if it happens to be the same resistance, then the time values will match. The values for those two time constants will match. All right, so we've looked at a lot with these circuits. These are really useful, interesting circuits once we put resistors and capacitors together. And it's because we have circuits now that are changing with time. Even though the battery is a fixed voltage, we don't have direct current. We have direct voltage or constant voltage, but the currents are actually varying with time. So these become really interesting circuits in terms of, well, informationally keeping track of using circuits to keep track of variations in the currents. All right, couple more slides here that we want to look at. Here is a diagram with a light bulb in here. We're going to close the switch. There's a capacitor over here, and when we close the switch, what's the light bulb going to do? Now, the light bulb is the resistor, right? So the light bulb is going to be, the power in the light bulb is going to depend on R times I squared. So that tells us that when the current's really high, the light bulb's going to be bright. As the current drops off, the light bulb will be less and less bright. And for an RC circuit, initially the current's going to be very high. So right when we close the switch, it's going to be as if the capacitor isn't even there. The light bulb's going to light up as if it were directly connected exclusively to the battery. But as the charge acquires, as the capacitor acquires more and more charge, we're going to find less and less of the voltage across the resistor. Current's going to drop off, the bulb's going to get less and less bright. Eventually it's just going to go to 0. So kind of an interesting example to think about. And then kind of our last topic here, just a quick discussion on measurements that we're going to make. This applies to what we're going to be seeing in lab. We want to be able to measure voltages, and we want to be able to measure currents. Now, we've been measuring voltages all the time, right? Way back since chapter 23, we've had our voltmeters out, measuring voltage differences between different locations. Now, we want to introduce the idea of an ammeter, and an ammeter measures current. It measures amps, and that's measuring current. Here is a circuit. I've got a battery here, I've got 2 resistors, I've got some junction points that are some connection points that I can connect to. And what we would like to do, for example, in this circuit is measure how much current we've got. Now, an ammeter, which is this circle with the A in it, ammeters are keeping track of current, and that means an ammeter needs to be part of a loop. So if I think of this as a current loop, current looping around through this circuit at all locations, well, I have to put the ammeter right in. So that becomes part of the circuit. So I have to disconnect and put the ammeter in. Voltmeters, meanwhile, we've been using voltmeters for several chapters now, we said. And voltmeters are kind of off to the side. So voltmeters can come in, they don't have to disrupt the circuit necessarily. Notice in order to put that voltmeter in, I didn't have to take anything apart. I just took the 2 contacts and made contact at a point on either side of that resistor. What voltage is that reading right now? And it's reading the voltage across resistor 1. How would I change that so that it's reading voltage off resistor 2? Yeah, so I could lift off my voltmeter, move it over to here, and measure the voltage across resistor 2. How would I measure the voltage across the battery? Lift these two contacts off and pick a point on either side of the battery to measure the voltage. Now this is only one loop, so what would happen if I move the ammeter here over to here? What if I put the ammeter, if I open up the circuit, take the wires out, put the ammeter in and reconnect it? It's going to measure the same current here as it would measure here. And if I put it here, same current here, same current. So summary, ammeter is in series with the current. Voltmeters are placed in parallel. And there's a problem. You're welcome to take a look at this. I think we are getting pretty close to wrapping up chapter 26 here for the day. So here's our summary. Let's see if there are useful things here. It says a source of voltage, or EMF, will transform energy from, well, our battery was taking chemical potential energy and converting it to electrical energy. A battery is a source of EMF, has an internal resistance. Resistors in series, so that's definitely important. We want to know if I've got a bunch of resistors in series, how do I combine them? We looked at that in yesterday's lecture. Resistors in parallel, follow the parallel rule. If we get more complicated circuits where the series and parallel rule are inadequate to solve the problem, then we have to start looking at circuits with junction points, writing down current equations, and then writing down some voltage loop equations. RC stuff, we looked at that today. The time constant for an RC circuit is just given by resistance times capacitance. And it must be a one-loop RC circuit to use the formulas that we've worked from. And then here, this is good advice. Avoid electrical shocks. So that's something to, and it's also good advice here. Don't leave spaces after your apostrophes. But the other good advice here is don't become part of a circuit. So what you don't want is you don't want to have current pass through you. So people say, well, what's dangerous, the voltage or the current? And what happens is, what we're seeing in all these circuits is that voltage drives current through something. So if somehow I make a contact with two whatevers, and there's a large voltage difference between them, even though I have a fair amount of resistance, there's going to be a little bit of current that passes through me. And so the current is what's disruptive and causes physiological injury. But it's done by having touching things that are at different voltages. All right, here's the ammeter and the voltmeter, and we just talked about those, and I think that wraps everything up for the day. It does. So that takes us through chapter 26. So we've done circuits for a couple chapters. Now we're going to go back and look at magnetic forces and magnetic fields. So we got chapters 27, 28 coming up, looking at magnetic effects. It's going to be fun.